So let me start. Today, we are going to introduce Cellular Automata. To do so, let us first define lattice. So lattices are actually regular arrangement of points in Euclidean space. So it forms the points, they form a regular network. What is so? Let us first define it formally. Formally, a d-dimensional lattice is a discrete additive subgroup of R to the power d. R is what is R? R is set of reals. Okay, so R to the power d is a set, and lattice is a discrete and additive subgroup of R to the power d. So this is the definition of uh, d-dimensional lattice. So d is here natural number. It is 1, it is 2, it is 3, it is 4, it is anything, any natural number. Okay, so it's like that. So if it is one dimensional, so lattice, then it is discrete additive subgroup of R. If it is two dimensional lattice, then discrete additive subgroup of R square. That is, so L is my lattice, and L is subset of R to the power d. And this L has to satisfy two properties. First one, this is very obvious that L is to be closed under addition and subtraction. See, since I have said it is a subgroup, okay, so R to the power d under addition forms a group, you know. R to the power d forms a group. So it is an additive subgroup. So actually the operator here is the addition, right? Now, to be a subgroup, so we need two conditions, that the members of that subgroup, the subset which form the subgroup, that to be closed under the operator. Here operator is plus, so to be closed under that operator, and so there should have the set should have that inverse of the element. So combining both these things, I have written this in this way, that L is closed under addition and subtraction. So if condition is satisfied, then I can get L is a subgroup of R to the power d. Next condition is there exists an epsilon which is greater than 0, not equal to 0. It is greater than 0, such that Euclidean distance between x and y, it is always greater than equal to epsilon. And here this is true for any xy of L when x not equal to y. And when distance is 0, it means x equal to y. If it is not equal to y, Euclidean distance between 2 points xy, that to be greater or equal to epsilon, which is a positive number. So these are two conditions. So these are to be satisfied by that L, the subset of R to the power d, right? The first condition is subgroup condition, and second condition is discrete condition. So we have emphasized this two. So take an example. Say z to the power d is lattice. So z means set of integers. So set of integers to the power d is a lattice. Why? Because so z to the power d, it's an integer vectors actually. See, I shall use the term integer vectors because z to the power d means d tuple, na? So it's square. So if x square, then xy. So it's a vector. So the elements of z to the power d are the vectors, integer vectors, and they always can be added and can be subtracted and after that addition and subtraction, the result is also an integer vector. Results are also integer vectors, so it's closed. And distance between any two vectors is at least one. So z to the power d, it forms a lattice for any d. D means 1, 2, 3. For any d, it forms a lattice because both the conditions are satisfied. Take a more realistic example. Say d equal to 1. So d equal to 1 means, so it's z. So z is additive group. We know it is an additive group. Why it is so? Take any two integers, say x, y, 1, 2, minus 1, minus 3, anything. So if I do addition, so x plus y is always again an integer. Similarly, x minus y also integer. So x plus y and x minus 1, they belong to z. So it's closed under addition and subtraction. And the second point, x minus 1, this distance is always greater than 1. You understand? So take 3 and 4. 4 minus 3 is 1. 1. Unless and until x, if x not equal to y, then minimum distance between x and y is 1. So both the conditions are satisfied. So z is a lattice. Now we can represent this in this fashion. So these are boxes. I'm saying that the positions, right? Say position means the one integer value. Okay, so it's like it forms a 1D kind of array, right? So you can think of a 1D 1D array, right? So 0, plus 1, plus 2, minus 1, minus 2, they're arranged linearly, arranged in a line. So this kind of arrangement we can see. Whereas if I take d equal to 2, you'll have this kind of loop, grid-like view you can have. So means x, y, say x comma y. So two values are there. So you can think of that it is a grid-like structure. So sometimes we call it grid. So it forms a grid-like structure. It's a regular arrangement. And see, we have started with this. The definition is a regular arrangement. You can see the arrangement of points, which are the black circles or black box here we have represented. Their arrangement is very regular, either 1D array or this kind of 2-dimensional view, 2-dimensional array. You can see, you can consider them. Okay. So z to the power d, conclusion is z to the power d is a lattice for any d, 1, 2, 3. I have given 2 examples, 1 and 2 only. But if I take arbitrary, subset of r to the power d, will it be lattice? This is an exercise. So test if q to the power d, q is a set of rationals. 1 by 2, p by q, we call it rational, but p and q both are integers. So test if q to the power d is a lattice. You can see if you take the rational numbers, so 1 by 2, 2 by 3, etc., then after doing addition, the result is also a rational number, right? And if you do subtraction, then also it will be a rational number. So first condition is satisfied, that you can easily understand that it is a subgroup of r to the power d. It forms a subgroup. It forms an additive subgroup, right? So next question is it discrete? It's exercise, you test it. Okay. Let us now consider, consider this z to the power d. Consider z to the power d. These are lattice. In our subsequent discussion, by lattice, we shall mean only z to the power d, or integer lattice. Sometimes they are called as d-dimensional integer lattice. So we shall discuss, throughout the course, we shall consider this z to the power d only. So let's consider z to the power d. Now, what we have seen, Z to the power D consists of several points who are arranged regularly. Let us call the points as cell, because the structure is cellular-like structure, right? As if the points are cells. Cells are arranged, regularly arranged, right? Now, what I'm doing, we are now placing an automaton on every cell, right? We are placing a finite automaton on every cell of Z to the power D, right? So same automaton is placed over that Z to the power D. Now, since it is finite automaton, so what we need for finite automaton, is finite automaton means it has a finite number of states, right? So we need a state S, and the transition function, right? If I represent, it mathematically, that we need two things. First, a finite set of states and the transition function, right? So for simplicity, I am considering here that is equal to 0, 1, 2, d minus 1. So d some natural number, d's 2, d's 2, 3, 4, etc. Some number d's. D equal to 1 is useless. So d equal to 2, d is greater than equal to 2. So for any d I'm taking, note that this is not mandatory to take s as set of integers. You can take anything. You can take character. You can take anything actually, any string. So when you talk about a finite automaton, then we don't say that what are the states. Point is, you need a finite set of states. That's all. So I have considered here that s equal to 0, 1 to the power 0, 1 and d minus 1, right? And consider the transition function is like this: s to the power m to s. This is my transition function. Now, what is m here? So let me discuss with a brief example. Suppose d equal 2. Consider d equal 2 means you have a grid-like view, right? And m equal to 5. So here in the right hand side, you can see there are 5 boxes. Actually, I have taken 5 boxes from the z square. Actually, you can have a grid-like view as we have seen in the slide. So so for one cell, suppose the blue cell here, that is cell under consideration, right? And now each cell, what I've said, each cell has a finite set of states. So therefore, the blue cell, the cell under consideration, it is having again finite set of states, right? Now, when I am defining R for this cell, I am considering the states of itself as well as some of its neighbors. Some of its neighbors. So here in this particular figure, I have taken n equal to 5. It means I wanted to mean here that so 2 left, right, up, down. There are 4 cells which are adjacent to the blue cell, the center cell. So how I am defining this R, the transition function for my automaton, for my finite automaton, it is taking input from the states of these the white cells shown in the figure. So in this way, I am defining transition function for for the grid, okay, or for the lattice. Now, if I concentrate on d equal 2 and m equal to 5, and if I apply R, then I can get this kind of view that I am applying R in the middle cell, means the transition function middle cell. So what transition function does? in a case of a finite automaton, transition function actually tells us from which state the automaton will move to what state. So state transition actually, it dictates the state transition of the automaton. So here, when I'm putting R, when I'm applying R in the middle cell, the state of middle cell is being updated by a new state. So in this way, suppose this is my construction. So we are now discussing about the construction. Okay. So what I've said till now, I have said that I am placing a finite automata over z to the power d. Same copy, I am putting same copy of the automaton to all the cells, for all the cells. So and since it is finite automaton, it has a finite number of finite set of states as well as transition function, in the transition function, and transition function is defined like this. So when I define a transition function, it considers the states of itself as well as states of its its neighboring cells, some of its neighbors. So in this way, I am applying R on the cells of the lattice. So we call them, as I've said, that M adjacent cells, they're the M adjacent cells, we call them neighbors. Okay, so from the word neighbors, we understand the meaning of it. So the adjacent cells. Now, if I apply R in this way, we'll get a parallel map, right? So in the first class, we are discussing about parallel map. Okay, so so similar thing. So I'm applying R parallelly, right? And when one cell will change its state, then all the cells will change its state accordingly. I mean, so the parallel application of R over all the cells. So we can get a parallel map from C to C, where, as usual, as we have discussed before, C is obtained, uh, uh, from uh, from S. This is actually cellular automaton. This is actually cellular automaton. So this is a parallel map. So let us now define more formally. So a cellular automaton is a quadruple. It has 4 components. First one is lattice, z to the power d. In our case, it is always z to the power d. Then a finite set of states, S, then M, then R. So as I've said that this is a d-dimensional lattice, and we shall call it cellular space. Same meaning. Sometimes we'll call it lattice, sometimes cellular space, right? And S is a finite set of states, and this is my aim. Aim I have written more formally what I've said just now. So aim is v1, v2, vm. It's the vectors. Okay, so v1 is a vector. Actually, if it is z to the power d, then z to the power d is actually the set of d-dimensional vectors. So v1, v2, vm, they are m d-dimensional vectors. This vector, now m becomes a vector which we call neighborhood vector. And this neighborhood vector is the property of the automaton, and each cell V uses that particular neighborhood vector to find its neighbors. So how it finds? Very simple. So for each V, what we do, we add V plus Vi. I means 1 to m, and here the condition is, I mean, it's obvious because z to the power d is closed. V plus Vi, vector V plus vector Vi, they always belong to z to the power d. It's a property of this subgroup property. So this we call neighborhood vector, right? And R is s to the power m to s is the transition function. In the C literature, we call them rule or local rule. So when we call the rule now, then we always mean the local rule. So in our further discussion, we shall call them rule of the CA, or it means the local rule of the CA. Why this local rule? You understand, because this R is applied locally. So each cell, each individual cell uses that R. A cell is not automaton. A cell is not a cell automaton. A cell automaton is collection of those many cells. But the cell applies R for its own purpose, applies locally. So R is called local rule of the CA. Now this is a formal definition of a cellular automaton. It has 4 components: lattice, set, neighborhood vector, and the rule. From the property of lattice, we understand the space. So is discrete here. Space is discrete, right? Because as I've taken z to the power d, space is always discrete, right? So it's a property of the lattice. And also we consider, also we consider here the time is discrete. So here space as well as time both are discrete, right? So it is a discrete system. Its evolution, its running is discrete. So it's called, we shall see it later, it's called discrete dynamical system.
Sir,
Please.
sorry to interrupt you. Sulfada has put some message on the chat box. So,
Yes.
can
So
you
can you?
please explain M once more? Just you please explain the definition once more.
Okay. I mean, since I am in presentation mode now, so I can
Okay.
see if you write something. Yeah.
Yeah,
See, what is the point? Please. What is M?
yeah.
Uh,
Please
yes.
explain M once more. That was the request.
Okay. Uh, M is the neighborhood vector, right? So uh, uh, which cells of a say z to the power d is the collection of many cells, right? So one cell changes its state using a local rule R. So the input of local rule is the state of the cell under consideration, as well as the state of its neighboring cells. Well, I have one example. I have one example. In fact, in the last slide also, I have given this one. Okay, if I go to the last slide, okay, if I go to the last slide, see here, here you can see that d equal to 2 and m equal to 5, that neighbor of, say here, blue cell, it has 4 neighbors, I mean 5 neighbors encoding itself. So this is mentioned by, neighborhood vector. So if I write in this fashion, that if my cell is V, is the blue cell is V, right? Then V1 say is the rightmost cell. Then it will be say 0 1. So I shall write it 0 1. Then the lower one, I shall write it -1. Sorry, 0 -1. Okay. So when I add these values, so I have V is a blue cell. If I add these values with that V, I'll get, I'll be able to get the the vector actually the location of its neighbors. Well, I mean, we shall come back to this position after the end. So I have one example. Let me go to there and then. Yeah. So now, uh, so what I've said, that space and time, they are discrete, and the automaton evolves. The automaton evolves in discrete space and discrete time. So uh, next, you know, next definition is a configuration. See, we have j to the power d, right? Now the cells, all the cells will have, you know, some, some states, right? So we can assign some states to all the cells, right? That assignment is called a configuration. Suppose I am applying one assignment, say called C. C is a mapping actually. So when I assigning something, we represent it in terms of some mapping. We're taking some action. So C is a function, right, which assigns the states. States means 0, 0, 1, 2, etc. That S, the members of S, to the cells, right? So this assignment is called a configuration. So if it is a say if my S is only 0 and 1, if S consists of only 0 and 1, and then if I assign 0 arbitrarily 1 0 or 1 to the cells of j to the power d, this will be one assignment, right? That assignment is called a configuration, right? So mathematically we can write this assignment is a mapping, is a function. So let us call it C. So C from j to the power d to S. Now if I get j to the power d to S, then I can get S to the power j to the power d as set of all possible configurations. So in set theory, what does it mean? Please see that one. S to the power j to the power d. What does it mean? It is mean all possible functions, set of all possible functions from j to the power d to S, right? We represent in this fashion. So S to the power j to the power d denotes set of all possible functions from the domain j to the power d to codomain say S. So the style. So domain is raised to the power of codomain, is a notation of representing all possible functions. Now, since configuration is a function or a mapping, so therefore j s to the power j to the power d is set of all possible configurations, right? Considering this thing, I can get a parallel map. Say s to the power j to the power d to s to the power j to the power d. So G is a parallel map. Just in the previous slide, I have said that G is a parallel map. I'm writing here more mathematically. So it is called as, we call them global transition function. So in the CL literature, two terms are used, local and global, and both are transition function. Local transition function, the transition function is actually named as rule actually, or called it local. And the other one, which is derived from that local rule, is called global transition function. G is nothing but the parallel map which we have already discussed. So therefore, we consider we can see that a cellular automaton hops from one configuration to another. Again, think of a binary system. So only 0 and 1, two states you have. Hmm. Only two states you have. Say 0 and 1, these are assigned in say z square. You can say z equal 2. Then you are applying one particular rule, local rule. Means each cell changes its state from 0 to 1 or 0 to 0 or 1 to 0, etc. depending on its neighbors, its present state and its neighbor state. Then what you'll get? You'll get another configuration, right? Means another combination of 0 and 1, which is another combination. So therefore, when you apply the local rule R parallelly on that j to the power d, you'll see that the system is hopping from one configuration to another configuration, then again another configuration, right? You can see it hops from one to another, right? So uh, uh, this is the meaning. Actually, we call it evolution from one configuration to another, etc. We call it evolution. And now, what is the relation between this, global transition and local transition? Suppose C dash is the next configuration of C. So capital G is my the global transition function. So therefore, C dash equal to G of C, right? The next configuration of C. If it is so, then we get this, that C dash V, right? Oh, there is a small mistake. In V means left hand side. In V there should be add vector symbol. That is missed. So C dash V is equal to R of C within bracket V vector V plus V1, then C vector V plus V2, dot C vector V plus vector M. What does it mean actually? What does it mean? See, in right hand side, I'm getting the state value C of how state value of the neighbors of V. How can I get a neighbors of V? I can get neighbors of V by adding the neighborhood vector, right? So I add V plus V1. So V plus V1 is actually a cell on j to the power d. C of V, I am adding C is a function, is a mapping, right? So I am extracting the state of that cell, right? This is the meaning of C, just defined above, right? Because C is the j to the power d to S. So if I give this input, I can get the S, I mean the state of this particular cell, right? In this way, this is for the neighbor of V1 neighbor of V. Then similarly, I find V2 neighbor, other neighbor, so V plus V2. Again, I get the state by C of V plus V2. In this way, there are M neighbors of a cell V. I can get the states of states of all the neighbors of V. Then I apply R. R is my local rule, right? R is my local rule. So I apply R on the states of its neighbors. So therefore, I get the new state for this V, right? Because R is a state transition, the transition function, state transition function, right? So applying R over this, state value of the neighbors of V, I get the next state of V, cell V, and this is applied for each V of j to the power d, right? In the both side, left side and rightmost side. So V is an error that should be a vector. V is a vector, right? So in this way, and cellular automaton evolves. I get a new configuration by using local rule at each cell. So this is the definition. In fact, this is the definition of the global transition diagram. Global transition function G. Okay, so G. So what I understand from this, G is obtained from the R. When you define R now, when you define CA, then R is provided. G is not provided. Cellular automata is actually cellular automaton is actually this fourth tuple, quadruple, not this G in general. But sometimes, since the behavior of that automaton actually expressed by capital G, so in many literature, the G is sometimes named as the automaton, cellular automaton. Okay, so don't get confused. By cellular automata, we mean the quadruple having 4 components, and from that one, G is derived one. Okay, so in short, sometime we call and the function G is named as cellular automaton. So this is the formal definition of cellular automaton. So now let us review, brief history of cellular automaton. It was actually, it is sometimes it is credited.
Sir, we have got another question.
So John von Neumann is credited as inventor of cellular automata. It is late 1940s or early 1950s. Von Neumann was working on cellular automaton. Actually, although I have written here Jonathan von Neumann, but in many places you will see the name of Stanislaw Ulam. Actually, John von Neumann, he was interested to develop a self-replicating machine, right? A self-replicating a machine which can replicate itself. That was the goal of, that was target of von Neumann, okay, in late 40s. And then it was advised, that actually Stanislaw Ulam, another mathematician, he advised that, okay, instead of developing a real machine, better you develop a mathematical thing, where he suggested that you take 2D grid, etc. Okay, so this grid-like structure, this definition actually, although von Neumann first implemented, although I have created here the von Neumann, but this idea is initiated by Stanislaw Ulam. And if we trace history, before the von Neumann, similar kind of idea was there. Okay. Anyway, in most of the literature, John von Neumann is credited as the inventor of cellular automata. And here the model is two-dimensional infinite grid of square cells, means d equal 2. Okay, so it's a grid of square cells, and each cell has 5 neighbors. In my example also I have given 5 neighbors, and each cell, okay, there's a mistake. So the cell, each cell there are 29 states. So that was the von Neumann's automaton. In fact, that was the first cell automaton developed. Okay, so like this one. So this is the 5 neighborhood interconnection. That the pink cell is still under consideration, and the navy blue, so the other neighbors. So in the cell automaton, the cell itself consider itself as a neighbor. So if I consider V as a cell, V consider itself always as a neighbor. It is a general notation, general style. And here, as von Neumann say, developed its, is automaton. It has 29 states per cell. So von Neumann died before publication of this work. Actually, von Neumann's work, recovered from its lecture notes of his students, who delivered some lectures. Some students from that this work recovered. He didn't publish this work. But the point is, this model has the capability of self-reproduction. In fact, von Neumann's target was this. And interestingly, this machine is as powerful as universal Turing machine. In the last class, we are talking about the Turing machine, and universal Turing machine is a Turing machine which can simulate all the Turing machines. So you can think that a computer is a computer which we work with. They are actually universal Turing machine. So this model, simple model, only 29 states per cell. Okay, so it is at least as powerful as universal Turing machine. Although automata, cell automata was automaton, this concept was developed in early 50s, right? Then some people, some mathematicians, some academicians, they worked with that in 70s. I mean 60s also some works are there, but it was popularized mainly by John Conway. Um, he was a mathematician, so he popularized this cell automata through his popular game of life. So in 1970, he developed this game of life, and here to develop this his game of life, he considered infinite 2D orthogonal grid of square cells. I mean the square cell actually, which we have discussed. Then only it has two states, 0 and 1. It's a binary say. One he named as alive and dead. So it's game of life. So it's alive and dead, and it has 8 neighbors. A cell here in case of von Neumann's case, von Neumann considers 5 neighbors, including itself. It has considered 9 neighbors. I mean, 8 neighbor means excluding itself. Actually, 9 neighbors. So 8 neighbors means these 4, another corner cells are also included. So horizontally, vertically, diagonally, adjacent cells. So total 9 neighbors were there. So after the work of Conway, so Cellular Automata became very popular topic of research. So then many people of many fields they joined in this research. So now I want to give an example to understand the working principle of a cell automaton and then best ways this Conway's game of life. So next we are going to describe this one, this automaton developed by John Conway, whose name is Game of Life. As I said, Game of Life is a cellular automaton with following parameters. Okay, here d equal to 2 means my cellular space is z square, and system is binary. The automaton is binary because S is 0 and 1. It has two states, and this is M. This is M here. I mean the question raised before, that will be cleared from here, I guess. And since there are 9 neighbors, so R, the local rule R from S to the power 9 to S. Okay, so look at the right hand left hand side figure, and there is a box. It's the middle box in red color. There is says cell under consideration, right? And around this, this cell, there are 8 more neighbors. So 1, 2, 3, 4, 5, 6, 7, 8. So they are all neighbors of this red cell, right? So including the red cell, there are 9 neighbors. So the local rule actually it is from S to the power 9 to S. So means it takes the input, I mean takes the present states of it's all of its neighbors. See, we shall call it these two terms I shall use in my further discussion, that present state and next state. So since it is evolving the sense of time, and since it is state machine, na, so time is there. So when I'm applying R actually, right? So state is being I'm getting a state transition, means from one state I'm moving to another state. So what I say, that before applying R, the state is the present state or present state, and after applying R, I get a new state. It's called a next state. Okay, sometimes we call it previous state and present state, like this one. So R is a state transition one. So time is there. So sense of time is always here. Okay, so R is from x to the power 9 to s. Now come to this M, the neighborhood vector. So here I have written the neighborhood vector. See the red cell. See how I have please follow this one. The red cell under consideration. What we do is a style that I'm considering this 0 0, the base cell. If it is 0 0, then the rightmost the right side blue cell is 0 1, right? If I consider x-axis and y-axis, it is 0 1, and then I am moving anti-clockwise direction. So then the upper cell is 1 1. Okay, I can point here, but please imagine the corner cell. Okay, so 1 1. How I'm getting 1 1? Considering the red cell as 0 0. If I consider red cell as 0 0, then right one is 0 1. Up to this right one is 1 1, and move accordingly. So then you'll get 0 1, right? X value is 0, then y value is 1. Then again the next cell, next leftmost cell, leftmost up. Okay, that corner cell, it is minus 1 1. They can go down, means you are decreasing the x value, sorry, y value. So minus 1 to 0, then minus 1 minus 1. This is the this is the another corner cell, minus 1 1. Again move next, 0 minus 1. Again 1 minus 1 is the other corner cells. Okay, so this is neighborhood vector. What is its implication? Suppose any cell position is given to me. Suppose my cell position is 2 comma 3. What I shall do? I shall add 2 comma 3 plus 0 comma 0. 2 comma 3. 2 comma 3 plus 0 comma 1. Then 2 comma 4. 2 comma 3 plus 1 comma 1. Another cell. 2 comma 3 plus 0.1. In this way, if I add the members of this, this vector actually, vector M, I'll get all the neighbors of my new cell 2 comma 3. So arbitrary location V is given. You add the members, so here V1, V2, V3, etc. with that V, you'll get all the members of that V. I mean, all the neighbors of that V. So this is the implication of neighborhood vector M, right? So I think, I mean, it's clear. If no, then I shall come back it after presentation. Okay. So this is uh, so this is my definition. This is my specification for game of life. Here I have just declared the rule, but rule is not defined. So to get a cellular automaton, you have to define the rule, you have to state the rule. So the rule definition, right? See, in case of cellular automaton, so some structure is given. So you have to specify D, you have to specify S, then you have to specify the neighbor. And most important thing is you have to define the rule. So game of life, for the game of life, rule definition is following. Very interesting. Say bath. See, now these words are used by Conway. Its name is game of life. A cell can die. Okay, it can be alive. Based on what? Based on the condition of its neighbors. Based on its environment. Conway designed this rule after a lot of experimentation. Okay, and you'll see actually. Say what is said. The first point is Barth rule. A cell, see here, dead and Barth. So I am using two values. So dead means 0. Here I have said 0 means 0 and 1, two states here. So two states here named as Barth and dead. I'm sorry, dead and alive. A cell with state 0 denotes the cell is dead. Cell with state 1 means it is alive. Right? In my rule definition, I shall not use 0 and 1, but I shall use the term dead and alive. So a cell is dead at time t, and that cell will be alive at next time. T plus or means next time step. If exactly 3 of its 8 neighbors were alive at time t. The cell itself is dead, but the cell can get life if the cell gets company from some alive members or alive neighbors. So interesting rule. A cell was dead, but it will become alive if exactly 3 of 8 neighbors were alive. Right? But since there is a birth, there has to be a death. Okay, so it's birth means birth says, so when a cell can get life. And so law of nature, if there is birth, there has to be a death. So a cell can die by overpopulation, overcrowding. Okay, if there are many inhabitants, okay, the cell cannot be alive. So if a cell is alive at time t, I mean, and four or more of its neighbors are also alive at time t. See here, it will be t plus 1, it will be t. A cell is alive at time t, and 4 or more than 4 actually, 4 or more of its neighbors are also alive. Then the cell will be dead at time t plus 1. Right? Interesting. So it cannot stay alive if you see that overpopulation will fail to breathe. So then the cell will die. And exposure. If a live cell at time t has only one live neighbor or no live neighbor, it will die. Why? Due to isolation. First one is overpopulation. Second one is isolation, because there is no. Okay. So this is the rule of death and survival. So it's birth and death. Third one is survival. A cell survives from time t to time t plus 1 if and only if two or three of its neighbors are alive at time t. Right? So these are three. These are the rule. Okay, they are stated in this way. I think all of you will appreciate that this rule is very simple. Once you have the grid, okay, it is very simple to program. Right? It will see the neighbor values. If you consider 2D array, two-dimensional array, right? So when you are at a particular location, you can get its neighbors. From that neighbor, in a small function, you can apply all the rules. Sorry, you can apply all the rules. Right? And then it will run. Now see what happens if this simple rule is applied in parallel to all the cells. Take an example. Suppose this is my I have sorry. So here black cells, the two colors I have used, white and gray actually. So so gray is 0. I mean dead cell. Black is live cell. Right? Black is live cell. So initially I have given this pattern as input. 1, 2, 3, 4. So 5 cells are uh, uh, are initially live. Right? Now see, I am applying this rule, this particular rule which I have just defined, to all the cells. Now consider the white cells. A cell is white means dead cell whose all the neighbors are dead. What will happen? See, look at the death rule, exposure rule. What it says? It says that a live cell will die if it has uh, I mean no live neighbor or zero life neighbor. That is about death of a live cell. But if a cell is already dead, then its transition is not written here, right? So therefore it will remain as it was, right? In the rule what I've written. So the transition of state, the condition which is not written here, that will remain as it was. So in white cell, if all the neighbors are white, okay, means a dead cell, if all the neighbors are uh, uh, are in dead state, are dead, then it will remain dead as dead. So although my z to the power d is infinite, if my pattern is like this, then rest part I need not to care about the rest part. Okay, they will always remain in state 0, in dead state, right? That you understand? So here what I want to mean here, I have to concentrate on that part where some cells are live cells, and the rest part where there is no life, they will remain dead as it was. Okay, so now consider these cells one by one. So apply the rule on the cells which is alive or some neighbors of the cell are alive. Okay, let us see what happens. There are 5 black cells, live cells. Now if you apply by your own, now if I apply, then I can get this next one. So you can see some states, there is a change. Just check. See here, the topmost one, topmost black. What is its condition? See, consider topmost black. It has 8 neighbors. It is alive, but it has only one cell live. Only one neighbor, actually. It has only one neighbor which is alive. That, the corner cell, uh, left and down. Okay, southeast corner. If you consider east, west, north, south, then southeast corner cell of the topmost black cell, that is alive. So only one cell is alive. So by the rule death exposure is a live cell, but it will die due to isolation because only one cell is live here. You can see the next step, because there's a next step, that cell is vanished, right? Also you can see that there is a, here in this configuration, the down, the belowmost, so the downward, that cell, the black cell, it was not there. In the previous configuration, it was not there. So go to the previous one. What was there? See, look that in the cell which became alive in the next time step, here it is dead cell because it has 3 neighbors. I can show you here, but it has 3 neighbors alive. So here, so this one, the new cell, new cell is, become alive here because it has 3 alive cells. Okay, so if you do it by your hand, then you see that some cells, then you can find that the cell, how a cell become alive, the dead cell become a live cell. So this I get, this configuration I get at next time step, right? Next time step we are, so again I'm applying, I'm getting this one. Again some kind of movement you can see, right? Again I'm applying, I'm getting this one, right? Again I'm applying, I get this one. Minutely observe that this pattern was my input pattern. So go to the first pattern. This is the pattern. This is the pattern. 3 consecutive black cells and then 2 black cells. Look at this pattern. Pattern is being changed. Then another change. A second time step, third time step, fourth time step. So at a fourth time step, I exactly get the original pattern, but a shift. Okay, as if it has moved. And interestingly, one interesting point also you can note here. Initially, it has, the automaton has only 5 cells, 5 alive cells, 5 ones. Here also in the whole evolution, so 5 cells remain alive. Although you have a rule of death, some have died, but number of death cells that become that's conserved. I mean, that remains same. So this is a glider which repeats itself every 4 iteration that I have uh, I have shown you. So this is your home task. Please do it by your hand. So if you understand game of life, the basic concept of cellular automata will be clear, right? And basic concept of parallel map. So this is a completely parallel map. Infinite number of cells, 0 to the power d, infinite set of cells are there. I am applying parallel map to all the cells, and I am getting this kind of pattern. So take another example. It's a glider gun I have taken from net. So there are very interesting. There are many simulators for game of life. You please explore them. So you see what happens. Say, so this is a glider gun, as if so two guns are there, some movements are there. You can see it's very interesting. You have to appreciate that it's very interesting pattern. Okay, this simulation is not done by writing the different other code. So here I have applied those three rules. The sub rules, in fact. Date, so where it will die, when it will become alive, when it will survive. That's the thing I have applied, and as a result, I am getting this very interesting thing. This is actually cellular automating. In fact, this is the beauty of the automating. Okay, by applying those simple rules, you are getting so complex patterns. So what we get from here, this is a zero player game. It's called zero player game because to play this game, to see the happenings of the game, what you need to just input the pattern. There is no other player. Means nobody is controlling death or life of the cells. So only single point of control, if you want to say, is there. That is during the start of the system. Second point is, as I've said, you'll appreciate that the rule is very simple. Automata is very simple. It's capable of doing self-reproduction, and it is have the capability of universal computation. It has been proved. Uh, so we shall come back to that part, computation part. But it has been proved that this game of life is as powerful as universal Turing machine. Means any kind of computation that game of life, that simple game of life can do. What's more, is a good example of self-organization. You can see you have given some pattern only. There is no central control. All the cells, they are independent in that sense that, okay, they run by their own. Nobody is dictating what to do, what not to do. They are taking input from its neighbors, and input the states of the neighbors, and produces some output. So there is no central control. You see, in case of what do you mean by central control? Say if you consider, say, any computer performs computation, but in a computer there is CPU called central processing unit, and then there is a control unit, right? So control unit, so every computation is dictated by that control unit. When to add, uh, and where to jump, everything is controlled, right? In fact, in last class, when you are talking about Turing machine, then also you see there is a final control that controls the movement of the head of movement of the head, and what to read, what to write. That is again maintained, right? But here there is no such central control, right? And it evolves from a simple pattern, right? A simple pattern, if you give a simple pattern, you will see is a chaotic, you know, some chaotic pattern, unpredictable patterns are coming out of this, right? So that you can see here. So these are the four important property. And game of life has a huge implication in science as well as in philosophy. Game of life, I mean, okay, and here what I've written here, that evolution is dependent on initial configuration. So the initial pattern I have said, that is called initial configuration, right? So that I've said. Anyway, what I was saying, that it has a great implication in computer science, in mathematics, in physics, biology, economics, philosophy, everywhere. See, you can see that from a simple pattern, from a simple initial configuration, right? Some complex patterns are are growing. So some have seen that as if it is a growth of bacteria, growth of virus. Okay, someone has modeled the game of life, helped them to model, you know, the you know the growth of bacterial growth. Economists, they they have seen it as if this game of life is dictating a growth of a city, how a city is growing, right? And computer scientists who are thinking that to get a good pattern, to get a to do computation, we need all a central control. We need something like that CPU, central processing unit. They're getting idea. No, the computation is possible. Universal computation is possible without having, you know, uh, such central control, and that actually led the philosophers to think in different way. So it has a philosophical implication. Anyway, so game of life has a huge implication. Uh, in fact, this parallelism, I mean, this no central control. There's the idea of von Neumann and Ulam, but since it is popularized uh, by this John Conway, and since the game is very simple, von Neumann's game was not so simple. His automaton was not implemented in computer due to its complexity. But this is very simple. So, so it has very huge impact. It was huge impact. Even today, people think of uh, this game of life. No, today I'm going to conclude, but as an exercise, so I have given uh, one example of evolution. You do it by yourself and test whether it's correct or not, and then you understand how the parallel map works. Then run the game. So in net there are several simulators out there. Spend some time to download them the game, or you can run them online and give some input by your own. Okay, then briefly I mean survey the game of life. Okay, so this is your exercise. That's all for today.
Uh, I have a quick question. Like, when we are
Yes, please.
considering that sales in that game of life, so what are the neighboring cell state we are considering if it is the corner cell?
Numeric celsius means,
Uh,
okay, let,
uh,
Let me go there. Okay, this one.
Yeah.
Mm.
Yeah, so we know that blues are all the neighbors of the red, but if we have to calculate the next step of the corner blue,
Mm.
we will assume for that the other neighbor.
Sorry.
Well, suppose we are trying to trying to compute the next state of the top left blue cell.
Hmm.
Okay, of the top left blue cell,
Hmm.
and what would be the value we should assume for the gray cells? Because for considering the next state of that blue corner cell, we have to also consider the gray cell value,
Hmm.
because the gray cells are also neighbor of those top
Right.
left
Right.
blue cells. So are we assuming any value for the gray cells?
No, no, no. It's zero.
Uh,
So this particular here, I have given the example. Okay. Let me use the board. Huh? Let me use the board. That will be helpful for me. Okay. I think it'll be good. Just let me use the board. Let me stop the presentation.
yeah, yeah.
Then let me use the board. Just a second.
Sir, I guess the question maybe is like, maybe I don't know.
Yes.
Asking
Please,
he's
please.
asking maybe that if in case of terminal nodes where the neighbor is not, it doesn't have all its like 8 neighbors, then what will be the rule for next step?
Uh,
All the cells which doesn't have 8 neighbors for them.
no. Shibpur, this
Yes,
is
yes.
huh?
Yeah, yeah. So basically, yeah, the kind of the edge cells or the corner cells
No. See,
where
I have considered d to the power d. There is no end. There is no end. Infinite, na? Infinite cell I have considered.
no,
There is
in
no
if
end.
we have to simulate, then we have to give some finite value.
Hmm.
For simulation, we have to give the finite value, right?
What's final value? Okay.
Means for
Shibpur voice is cracking.
yeah, what I'm saying that if we are trying to do some kind of simulation
Hmm.
programming, so in that case, probably what we can give an input as a 2 by 2 matrix. So since it is a 2 by 2 matrix, means it's a two-dimensional matrix, it will be a finite matrix, finite elements. So in that case, there will be some cases cells are terminal or corner.
Okay. In my discussion, I have not said anything about the finite system. We shall discuss because especially when we apply automaton for as technology, then I have to declare this one. But if you want to simulate this system, then you have to take a big array, and that has to imply that I mean this big array has to imply that you have infinite space. How it can be possible? It's not very difficult. I can tell you. Just let me use the board. Board is a good one. Can you see my board? Yes. It's okay.
Yes.
Hmm. Ah, see, I can tell you the answer intuitively. See, I will say big array, big space I have taken, right? I have taken a big space. Hmm. You know. Now here, my initial configuration is here, right? Initial configuration is here. This is my initial configuration. I mean, initial configuration means The non-zero values are here, right? Non-zero values are here. Now I apply the rule. What will happen? See here in the first case I have said, suppose this consider this cell. This cell is 0, its all its neighbors are 0, so they will remain 0. So there is no problem with other cells whose neighbors are 0. So they will they will remain 0, right? Always. Now who can be non-zero? Who state can be non-zero? The cells under these cells or its neighbors, they can be non-zero only, right? Not beyond that, right? So in next step, at most these cells can be non-zero, and next steps, at most these can be non-zero in this way. Why? What I want to mean here, that if I start from this kind of configuration where finite number of cells are in 0, are in state 1, in my successive run, it will remain finite always. It's a, you can understand from the rule, because this part they are always they all are 0. Only the neighboring part they can be non-zero, so they are growing. So what can happen? Step by step they will, they may grow. Not always, they may grow. Okay. Now if I take a big array, okay, I can compute that how much time it will take to reach to that end. Okay. Suppose I want to run the simulation for say 100 steps. Then I have to take the array in such a fashion so that in 100 state I'll fail to touch my boundary. This is style if I want to implement this kind of system. Right. So this kind of configuration we shall discuss later. They are called finite configuration, because finite number of cells they are in non-zero state. Right. If it is a finite dense system, nothing will be different. So in the particular case, there is no issue. There is no such problem. Yes, Shibpur.
Yeah, so basically we are assumed that whatever the neighbors are, if it is not uh, defined, then it is 0.
No, no. All are defined. So what I have said, I have said that there is a assignment. So see, I have said 0. Sorry, C z to the power d to s. I have defined this one. So here for all
Okay,
the
okay,
elements
okay.
of Z is defined, assigned. A cell cannot exist without state,
Mm-hmm.
but I have assigned zero only. In the PPT, in the slides, so
Mm.
gray cells or white cells, they are assumed that they all are 0. All are set 0. There is no question of undefined. So all are defined. I mean, undefined,
Okay.
the word is not right, but there is no question that there is the assignment, because I have assigned this C. This is my C. So that part is clear, that the
Mm-hmm.
neighbors.
Okay.
Okay.
Yeah, neighbors are clear.
Okay. Any more question?
Okay, another question is
Yes,
that
please.
while we are saying that it is a configuration, so for a single element, we are considering that state. And for a collection of element, the next state, like the collective state, we are saying it configuration.
No,
Is this statement correct?
no. Configuration is
Okay.
collection, collection of all states, not some. Okay. So I am
Yeah.
configuring the automaton. This configuration means I am configuring the automaton, and this automaton. How to configure this automaton? By assigning some values, right? So we call it configuration. So it is true for any kind of automaton. Automata, it runs automatically. So by putting some initial value, so we configure the machine, right? So it's called configuration. So this is a configuration, right? I'm configuring, and here in a zero player game, so the machine runs. This is a machine, so machine runs. right? So I have to configure the machine. So how can I configure? By assigning some state value states to all the cells. So I call that is an as an as configuration. So mathematical is an assignment. It's a function.
Okay. So it is all collective states of all the. Suppose we have 10 cells and we have individual state for each of the state.
Sorry, please.
States of all these 10. Hello.
Yeah, states of.
Yes, means what I'm saying that so configuration is basically collective states of all the elements. So if we have 10 cells,
Uh,
then each cells has their individual states.
uh,
Then collectively those 10 states of those 10 elements we can see the configuration.
okay, but there is a sense of time at a given time,
Yeah.
right? Because it is assignment, so
So
I'm assigning
basically a
one.
snapshot, right? For a
Right.
configuration is a basically a snapshot.
Right. It's basically a snapshot. So if you say the collection, that's okay. It's a really collection, but collection at time t. So some at time is needed.
Yeah, state is also at some point of time.
Time, yes. A state machine. When I'm saying state, it is I'm referring to time. Hmm.
Yeah. Okay. Also, can you please go to that slide where you are defining something with epsilon,
Yes, the lattice part.
the lattice one? Yeah. Yeah. Yeah.
But the question is that epsilon was greater than zero.
No, I have just a small question that in the lattice part there exists a epsilon
Yeah.
which is greater than
Zero.
0,
Hmm.
and then we are just calculating that the Euclidean distance of
Right.
x minus y
Hmm.
greater than equal to epsilon. So
Hmm.
instead of that, if we write it is the Euclidean
Sorry. Instead of that.
y, if
Sorry.
we
Instead of
write
that.
that Euclidean distance of x, if we write Euclidean distance of x and y is greater than 0 without introducing epsilon, will that be incorrect?
Yeah. Well, no. But it will be by non-zero, greater than zero. Euclidean distance should not be
Yeah, so
without it.
without introducing epsilon, we can also, yeah,
That's possible.
so we there's a same thing, right?
Right. Euclidean distance of any two points should be non-zero. Non-zero means Euclidean distance means always positive. I mean non-negative. So it should be non-zero.
Yeah, so basically x and y are two distinct point that
Right.
we are actually trying to make,
Right.
right?
Right. Right. So it is making it discrete. If it is a
Yeah,
two different points, but suppose two different point, but difference is zero. Distance I mean is zero. That is not allowed. That's the point. If two points are distinct, so they have to adjust some distance. Okay, point are distinct,
yes,
but
yes.
distance is zero. That's not allowed. That's the point. Did understand from
Right,
concept?
right. Yeah. So there is no overlap. So there is no overlap basically. 2 points.
Okay, okay. You test whether Q to the power d satisfy this one. So if I take rational set of rationals, whether this property is satisfied, you test. Okay.
And when we are saying that z to the power d,
Mm.
so that time we are considering only the integers. So it cannot be, so since we are considering integers, so the lattice is basically a discrete, right?
Yes, yes,
So
yes.
it is not possible to consider r to the power d, or is it possible?
Mm, no, not you. Let me know whether Q is possible. If I consider Q, okay. This question will be clear if I from that one. You try that one. If it's continuous, in case of continuous system,
Hmm.
na, you'll find 2 distinct points where it is
Hmm.
distance is 0. That is the point. That is the issue actually. That will find in case of that one set of Q actually, and that will find in case of Z sorry, R to the body,
Okay.
R to the body, not Z to the body, R to the body.
So r to the power d, basically we can find 2 points at same, means without any distance.
And we find, yeah. You
Okay.
test with Q, it will be clear.
Okay. Okay.
So Q means what is Q? I mean, set of rationals means P
Hmm.
by Q. So
Hmm.
small p by small q is the where p and q both are integers. Okay, this is
Hmm.
the definition of rational number. If I take set of all rationals, say 2 by 2 is rational, 4 by 4 is another rational, or 1 by 2, 2 by 4 all are different rationals. So and see that whether they are getting any problem, right?
Right. Right.
1 by 2 and 2 by 4 are the same? Not now. I mean they mean same, but you see, definition of rational is p by q, where p and q are two integers, right? This is the definition
Yeah.
of real number.
Yeah.
And now p equal different, q equal different, so you get two rational numbers. So 1 by 2 and 2 by 4.
Correct. Correct.
Both
Yeah.
are actually same. I mean, sometimes in reality we mean them they're same. But if you stick to the definition, they're the two different elements. Na?
Hmm. Yes. Yes.
And see whether this is getting problem or not. It should get problem.
Yeah, I have not thought in this way. I was thinking like if their difference is more coming closer to zero, then will there be any issue or anything?
Just
Like
check.
it tends to zero or something. So very small distance, but that should not be an issue if still it is greater than zero.
Yeah, yes.
Okay, and I had the previous question regarding aim. So basically, what I understood that uh, we are we have the rule that is converting from s to the power 9 to s for this
Hmm.
game of
Hmm.
line. So
Hmm.
basically, nine
Yes.
element, from 9 element we are converting to one element.
Hmm.
So aim is basically defining which 9 elements. That's why we need aim, right?
Yeah. In this case, we know the when the which line are there. The same in general, which line actually. Hmm.
Yeah, so basically significance of M is, since it is a vector, it is basically uniquely determines that the location, the
Right.
position of those 9 elements.
Right.
And rule is basically considering their current state and converting to the new.
Right. Next step. Next step.
Yeah, next. Yeah. Mm.